So you can still talk. Yeah. All right, guys. So maybe we can get started. Make sure everything's okay. Age match. So we have our final session, STINT, the second day, which is a panel session entitled BP versus our IP visions. The panel, I'm going to introduce each of the three panelists. I will read out the bios up loud. And then, yes, I will go basically one by one. So one of the panelists is sitting here right here with us is Leigh Torgerson. So Leigh leads several efforts in the development and operations of spacecraft systems with an emphasis of end-to-end communication system technologies. He has over 45 years of experience in team management, aerospace system design, digital and RF electronic systems, integrations and testing. He has been with JPL since the 90s and he's currently a space communication networking architect in the communications architectures and research sections at JPL. He has been the DTN team since his inception, co-authored the DTN architecture FC, managed JPL core engineering support team for the DARPA DTN program, and currently is leading developments of end-to-end communications protocols, networking, testbeds to facilitate the infusion of DTN into JPL deep space communications and mission operation systems. In addition, he's developing a Mars DTN relay network operation systems and conducting extensive ion DTN ion hardening testing to ensure the maturity of NASA baselines ion DTN software. His professional experience includes serving as a United States NASA naval aviator and 10 years of the Lockheed Skunk works as an avionics flight test engineer and avionics department manager before joining NASA JPL. So welcome, Leigh.
I was too lazy to write
you have a little
small bio, so I just preferred doing a paper.
That's a very well-deserved bio, Leigh. Thank you for joining us. Thanks, Leigh. We have so, by the way, I will introduce this one each of you guys, and then I will leave you the room for presenting. So just give me 1 second. I will introduce our second panelist is Erik. Erik Kline is a network software engineer at Illyria Technologies and a long-term contributor at the IATF. Since 2020, he has been the IATF Internet Area Director, responsible for IPv6, NTP, and the standardization of eBPF. Recently, he took over as a responsible area director of DTN within the IATF. From 2007, he worked to migrate Google infrastructure and services to support IPv6 and help evolve the Android core networking stacks. In 2018, he had the chance to meld his network experience with his undergrad aerospace engineering degree as a contributor to Loon's Temporal-Spatial SDN, a project that continues at Illyria as Spacetime. So also, welcome, Erik. Thank you for joining us, the panel today. And let me finally introduce our third panelist. His name is Marc Blanchet. Internet engineer for 30 years, president of Piageny, co-author 17 RFC, co-authored 20 IATF working groups, including DTN for many years, former IAV member, currently leading the project to investigate the use of IP in deep space IP. So this is Marc Blanchet. So thank you, guys. I invite you to join the table.
Erik,
all right.
The Empire. There is
a cage match.
Jedi. All this. Let the past die.
Apropos.
Kill it if you need to. Join me to rule the universe with IP.
Guardians of the Galaxy in person.
Let's roll it with engineering.
All right. So the idea of the panel, guys, is to we have a short talk of each of the panelists. We have Leigh first, Erik afterwards, and Marc at the end. And then after the second part, we'll have an open discussion session where we also take questions from the audience and so on. So with that said, I leave the floor to Leigh to present. Your slides are on the desktop. If you just want to Windows D, then go desktop. You should be Leigh. That is the one there.
Okay. Okay, this is truly preaching to the choir, so I'm going to go very, very fast. If anybody has any questions, just stop me while I'm talking. When I have summer students in, the first thing I explain to them is that why internet protocols generally do not work in space. Period. No, I mean the original thing, seriously, is that the key assumptions in the internet design over the years, and I'm not an expert, but I pretend to be one. Networks are richly connected. That's kind of a given for the most part. Networks have short delay. Data links are symmetric and bidirectional. You seldom have half duplex or anything like that. Ethernet fiber optic cable is supposed to be bidirectional, symmetric. Links have low error rates, and that if there is loss, it's due to congestion instead of corruption. Because normally what happens, everything gets to a router and it's too busy and it just throws things on the floor. Everybody assumes that network nodes, the routers, are trustworthy because they live in somebody's back room and the server room and with a combination and everything, and they're not reachable by ham radio operators and the normal high school hackers, and that all of the connection model is end to end. So no matter how I route things around over to Scott, I have to have a return all the way through the network back to me from Scott. So end to end. In space, what we found out very quickly when we started looking at how to do internet in space, which is what Vint Cerf was concerned about, that nobody was looking at internet in space. So when we started this whole thing 20 years ago, that was kind of the impetus. We have a sparse network. It's asymmetric. You end up with half duplex, or as Roy was saying yesterday, the deep space network, the beam it can see the entire planet of Mars, and it can receive 5 different spacecraft signals down, but it can only talk to one right now. They got a new program called MUPA, which is multiple uplink per aperture, but they're going to try to cure that eventually, but that's in the developmental stage. So you end up with unidirectional links in space where it only goes in one way, or it goes one way and then you reply back later on when the link is available. When we lose data in space, it's usually corruption, or the antenna's pointed in the wrong direction, or cloud has come across your K-band uplink or whatever. So it's usually corruption, not congestion. And there's a lot of loss due to orbital geometry. The stupid spacecraft's on the other side of the moon or the other side of Mars, and you can't see it for 90 minutes. You send it a message just as it disappeared over the horizon, and then you got to wait till it comes back around to get the return. And then, of course, inordinately long propagation times. It's 40 minutes one-way light time to Europa. And we just did a project with the Europa Clipper people to simulate 40 minutes one-way light time for their CFDP transmissions so that the spacecraft team could get used to the idea of sending a command and waiting for an hour and a half before the return came back that the file was received. And, of course, insecure, we always had security by obscurity with the Mars programs because not many hackers have a 34-meter dish in their backyard. But you can see the moons right there, and you can build a little Yagi and hack into Mars all you want. So the original DTN design elements were don't replace the terrestrial networking protocols. Put an overlay network on there, and the overlay network DTN can then sit on whatever underlying network you bring to the table. So it runs over terrestrial internet just fine, UDP quick, all the way to New York. I mean, he'll tell you all about that. But if it also runs over radio links, and as we were talking about lunch today, you can take a bunch of DTN traffic and run it into a memory stick, pull the memory stick out, walk over or drive over to the next computer, stick it in, and it'll just pick up that and go from there. So you can have a Nike net in between. You've got to deal with loss and delay because you don't have end-to-end paths. You have to have hop by hop kind of a design principle. And we decided we wanted to fix what the IP design missed 40 years ago, which was basically security and quality of service. And we've already got quality of service handled right there, typing away on our laptop. Quality of service and security right behind it. So we're doing a really good job, I think, in the DTN world addressing some of those initial problems. Let's put it in now and get it over with. We have to deal with different kinds of routing needs because you can have pre-planned contact plans for space use. You can have continuous all the time for terrestrial networks, and you can have opportunistic contacts for IoT. And there's a number of different. There's probably more PhD thesis work going on routing methods in the world today than you can imagine. We got lots and lots of different routing methods besides contact graph planning. And we also wanted to design in the network management security key requirements, security key management, and that's a real big can of worms because we know how to do BPSec, we know how to do encryption, we know how to do integrity hashes and that sort of thing. Nobody's got an idea of what to do with the keys and who makes the keys. In the United States, it's the National Security Agency has to give blessed keys out to NASA, and then NASA's got to figure out how to pass those out to the various projects. And they haven't done that in years or ever, so they're not really sure how to do it either. So we have delay tolerant key administration for the future space internetworking, but we got a lot of work to do between now and then to make key management really work. We've got asynchronous management protocol that Ed Bahrain company of they keep changing the name of it, but it's just, I always tell people it's like having a Cisco router and you got the software that allows you to get into the Cisco router and fiddle around with the settings and get the status. So the DTN AMP does the same thing for DTN nodes. It figures out what's happening inside the DTN node, and you can change its state using that. If the DTN node goes down, you still need other ways of getting into that host computer to find out what's going on. Is the node crashed? Did we need to restart the computer? That sort of thing. So there's a lot of work going on that score. So we have some unique environmental conditions. I'm not going to just read all these to you, but one thing is if I've got a 4-hour DTN pass, meaning I've got 4 hours to talk to my spacecraft, that doesn't mean I'm going to use all 4 hours for DTN, because the first hour I've got to do receiver sweeps and ranging and Doppler measurements and a bunch of other stuff that has nothing to do with data transfer. And then a lot of times the spacecraft wants to use like the next hour to get all this high priority standard, old legacy telemetry back, because they don't quite trust DTN, so they don't want to, have everything dependent on DTN. And then they might say that, okay, for the last 2 hours, you can have the last 2 hours for a DTN contact, but out of my 4 megabits per second downlink, you can have 2 megabits for DTN, and I'm going to have the other 2 megabits for AOS downlink telemetry. So the contact plan for DTN says, well, okay, my contact's 2 hours long and my data rate's going to be 2 megabits. And then the DSN gets the plan with your contact period is 4 hours and it's 4 megabits. And when the traffic comes down, it gets split off by virtual channels. One way goes to the DTN node and the other way goes to Space Link extension, and the way we've done it since Apollo days. Latencies are all highly variable, time dependent. There's cruise phase, there's in orbit phase. I mean, you can talk to the guy for forever on the way to Mars, and then once he gets to Mars, it's every 90 minutes. It goes around the planet. Or if you get to the moon, it's going to be some time to get to the moon. A lot of the lunar programs like KPLO spent 4 months getting into orbit around the moon. And it was in an orbit that faced the Earth the whole time, so you could talk to it whenever you wanted. And then it finally got into its polar orbit, and then now, depending on where things are, that time changes. So it's not statistically computable, so it's really hard to automate. and that's another research area that we can all think about. Automatic routing is difficult. Opportunistic routing. The problem with opportunistic routing is if a spacecraft just like pops up all of a sudden from like another country, another mission or something, and it's on its extended mission and says, "Okay, I'm volunteering to be a relay orbiter around this planet," and you add him, and if he opportunistically just shows up in the local network and goes, "Hi, I'm Steve, and I'll be your router today," it can take days for that routing information to propagate through the whole network. So that's another variable thing that the delay does to you. But you don't have that much delay in the internet. The IPN addresses are numeric for the reasons of wanting to be efficient on your link. So they originally in VPv6, it was compressed bundle header extension, and instead of having an address that looked like a URL, DTN:// spacecraft name / blah 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 blah, for the sake of link efficiency, which is a really important thing in space projects. We put in the IPN, Interplanetary Network naming scheme, which consists right now of a node number and a service number. And the service numbers, I always tell people the node number is kind of like an IP address and the service number is kind of like an IP port. So the local node registers, an application starts up and it tells the DTN node, "I'm here, anything coming to service number 42 goes to me." And then the BP application, if it's addressed to service number 42 or 65 in the case of CFDP, it spits it up to the, whichever application registered that. Same way it works in the internet. But it's very, very small. In fact, an IPN address is smaller than an IP address, especially a V6 IP address. DNS-like systems take too long to update. Right now, if I change an IP address on the ground and the computer goes down, I bring another computer up and it's got a new IP address, but it's got the same name. The DNS system can take, up to like 3 days usually to propagate through all the DNS nodes. So we got to watch out for that sort of scheme in the DTN world. They keep talking about wanting to have a registry of IPN addresses in IANA or SANA. And if we got to be very careful on how we implement something like that, because when something changes, you want to be able to change the contact plan, let everybody know right away what the change is and know how to propagate that change. So this is the last slide. I think the ION DTN software design philosophy, since the software designer is sitting right there with his counterpart for BPSec sitting behind him, they should be up here talking about this. But we needed hard memory allocation limits because of the way spacecraft with real-time operating systems work. They say you can use this part of memory and don't dare step outside of that boundary. So that means you got to do your own memory allocation scheme, which is a pain in the neck, but it's a necessary evil until such time in the future where we've got unlimited Linux computers in spacecraft with 64 gigabytes of RAM. Modular and robust operation, there are different processes within the ION software. You can change some parameters while you're running the node without having to restart the node, and that's very handy if you want to change the operation. You want to change the LTP engine parameters and how big segments ought to be and how big blocks ought to be and that sort of thing. You can do that on the fly. The memory allocation, you have to stop the ION node and restart it. So there's mutable and immutable properties of the nodes. And no matter whose DTN implementation it is in a spacecraft, you're going to have similar problems or similar constraints, if you will. One of the important parts of that is if a module if a module in the Ion software turns out to have a bug for some reason, or it's misbehaving, you can stop that process, still running the Ion node. You can stop that process, swap out that module, start it up again. And so it makes it very efficient makes it complicated to use, but makes it more efficient to use. Independence from native IP socket support, I won't talk about that too much. And then portability and minimal footprint for static linking. That was another important design philosophy with the Ion DTN software. So that's about all I need to say about DTN.
Thank you, Leigh.
And just arrow keys, fine?
Yes, yeah, should be okay.
Those work.
Page
okay.
down or?
Page down, or just arrow down, arrow up is what I was using.
Hello. Thank you very much for including me today. Please, and thank you also for maybe bearing with me. I think before the first session this morning, I was enjoying a root canal. So my first priority is to actually try to remain coherent. And then my second priority would be to maybe just share some thoughts as a longtime IP guy, especially an IPv6 guy, having come to Bundle Protocol about 5 years ago, 6 years ago. As Juan mentioned, I was a networking software engineer at Google for 18 years. I wrote a bunch of the IPv6 support for their public services. The sort of design for was involved in the design of the data center. I wrote the support for YouTube streaming on IPv6 and Google Public DNS and authoritative DNS and a bunch of other stuff. I also did a bunch of stuff for the Android networking stack for about 5 years. If you have an Android phone, possibly some of my code is still in there, so maybe I should apologize. But anyway, I got the chance to come to Bundle Protocol when I joined Loon in 2018. We were at that time looking at support for DTN for some of these IoT LoRaWAN use cases. We were thinking about putting a LoRaWAN payload on the balloon next to the LTE 4-sector antenna, and for reasons completely unrelated to technology, that never happened. And as I'm sure many people have experiences here, and of course Google X pulled the plug on Loon during COVID. But the SDN team that orchestrated the network and built the topology at layer 1 lives on at Illyria, my current company. I also I thank Rick Taylor for helping me with some of these slides, helping review at them as well. So my observations, probably there's nothing new here for many of you, but I mean, I think of IP as like layer 3 versus VP as a messaging layer, completely separate. IP has datagram boundaries, but no inherent sort of message payload boundary. Unless you have a fragmentation header, IP has no idea where your real payload sort of begins or ends. Whereas, of course, in VP, you have pretty clear message boundaries. In an IP, you have addressing and routing are integrally tied, right? There's the Internet Engineering Note 19. Some people like to talk about to say, addressing isn't routing and routing isn't addressing. And that's fine, but they really are like integrally tied and they cannot be separated. Whereas in VP, you have very clear separation between addressing, the address of a message, destination of a message, and how it should be routed. I think this has mobility benefits that are quite interesting, subject, of course, to control plane updates. But you could easily imagine moving into an area and finding bundle protocol messages waiting for you, or waiting for you specifically, or waiting for you just because you're in that area. And it has none of the concerns that IP mobility has. The battlefield is strewn with the dead bodies of IP mobility solutions. So I think of this as very, very interesting for bundle protocol. Of course, delivery address resolution start time for IP, like when you call your connect call, when you call DNS or get host by name. Whereas you have the option to re-resolve your topological destination at every VP node in a delivery path. For IP, you really only have retransmit at the source, and you don't even have that at the IP layer. That has to be guaranteed to you by some other higher layer, like TCP or QUIC above UDP. whereas you have the option in BP to retransmit at intermediate nodes if you've like relayed something along the way, right? This is an important distinction that was novel to me. One thing I think BP IP has is de facto standard APIs for use. Sockets, the BSD sockets API is well known, well universal. This is one of the things that I think I find perplexing, but understandable about cloud environments. Many people want to have their cloud environments have sort of a pseudo network, but they don't want the internet. There's a lot of security panic and locking everything down and firewalls and VPNs and whatnot. And they really don't want the internet, but they do want internet technology because everything is already written to it. It's very easy. There's like 40 plus 50 years of history of code that you can use. I don't think that BP doesn't have this yet. Doesn't have that sort of broad adoption and experience. I do see that there's plenty of room for both. The IP is obviously proven for terrestrial networking. The BP, I think, clearly in this community is well known for its site heritage. I strongly suspect it's less well known outside of this community. It has delay and disruption tolerant properties. I think that you can get delay properties, but disruption is kind of a different beast. I think of bundle protocol as very interesting as a messaging layer, and I would like to see it sort of have a broader life as a standard messaging layer. Store and forward is obviously important, but it's not really mandatory to use. It has a robust extension mechanism, which I think is also an interesting area to explore. Unencumbered by middle box interference, we cannot deploy a new IP extension in the internet today. You could deploy it in your own network. You could deploy it in your best friend's network if you coordinate with them, but you really can't use it. You really couldn't deploy that today. Bundle protocol has no such restriction yet. And so, I mean, I will stake my engineering career on this highly controversial position of the right tool for the right job. We'll see what happens. Just some random ideas for some bundle protocol things that I think could be useful, mostly in a terrestrial context. First of all, I think we should have a data model for a rib and a fib. And if we have a data model for a rib and a fib, then any number of control planes and control plane extensions can be envisioned so long as they transmit the required information that fulfill a rib and a fib update. This could then easily become something that's in DNS for terrestrial use, wherever DNS would be useful, obviously not in certain long context links. I think it's entirely possible to have a BP version of SMTV's MX record, for example. As a standardized messaging layer, I think we need a document to give application advice for people. I think there's probably a lot of experience in this room about how to write an application that uses bundle protocol, uses DTN. I don't know that any single document exists to sort of propagate your collective experience. I think that could be of value, and it could easily just wrap up a whole bunch of other stuff, and we wouldn't have to have a specific X over BP definition. You could, if you're bound to HTTP, you could just use 9292 binary messages, put them in a bundle, and follow the other application guidance. Similar to what, along the lines of what Brian was saying yesterday, I think the integration with the broader sort of common internet PKI is of value, particularly for terrestrial uses. I know that not all of the problems may be solved or for non-terrestrial use cases, for long duration links where keys can't be updated or can't be rotated quickly enough, but it is battle tested pretty hard over the last couple of decades, and bundle protocol should certainly steal anything and everything that it can. So I think there's possibly some more interesting CLA options that might be defined. I think you should just be able to plug two things together on Ethernet and send bundles across without any other configuration than that. But and then I would like to see, as a standardized messaging layer, some sort of more. It would be great to have more application use, more adoption. I'm aware from IPv6 that there's a tendency to try to want the killer app. In IPv6, I learned anyway, that there's no end to the number of hoops people will go through to make something work with what they have. And so the existence of a capability is easily replicated and seldom unique to a system. So anything you could do in V6, you could make work with an awful lot of tax paid through CGNATs and through other sorts of things on IPv4 if you really wanted to. But the performance of that connectivity is the killer app. The connectivity itself is the killer app. The fact that you can communicate it all, and you can communicate in a performant way, is itself a killer app. So, lastly, I know this is largely a CCSDS crowd, but I would be remiss in my duties as an area director for the IETF to not invite you to join us. There's a DTN working group, these mailing lists, there's a mailing archive. We have a IETF meeting in Vancouver next week. Remote participation is available. The DTN session chaired by Ed is on Thursday morning. And all IETF sessions are recorded. They're free on YouTube. You can go there. There's a YouTube playlist for every conference. So you can, they get updated kind of quasi real time, usually by the end of the day. So by the end of Thursday or the end of Friday, you should be able to rewatch whatever we talked about on Thursday. Anyway, thank you.
Thank you, Erik.
I think the joke is done now.
Let me get this out. Yep. Oh, yes.
Good afternoon. Kylo Ren here. This work has started a couple of years ago when I was getting concerned about what people have been showing, for example, today and yesterday about things yet to be done within the BP environment. And then I started to look at the initial assessment that Vint and Scott and Leigh and Keith and others have done. And I was kind of revisiting it and see, well, maybe, it's 25 years now later. Maybe this is, maybe it needs to be reassessed and see where he goes. And so I actually had a few friends, internet, engineer veterans that helped me out. And before this work was actually published, we wrote a draft and sent it to probably 30, 40 different people to get their comments. And, nothing bad came out. So, well, there it goes. So one asked me to present a bit of it. I have like a slide deck of probably 150 slides. I'm not going to present everything. So there's topics that I removed. Happy to answer any questions because we're talking about the whole stack. So there's point of view of everywhere, and I don't claim to have answers about everything, but I've been surprised every day about finding that, seems to be working. So I skip a lot of things here to go down to the deep space IP stack, where you see that TCP is out as found, 25 years ago. So we're going to use IP and UDP. That UDP give us, the protocols that runs directly over UDP. Give us CoAP, which is a kind of a HTTP-like semantics for IoT, and then QUIC, which gets us, apps, funneling media, and HTTP over any kind of link. So I used to go with a longer presentation to go through each level and discuss each of them, and also. We have now a pretty large set of simulation data. I don't remember exactly how many I put in the slide deck, but probably just a few. So IP has the notion of time or no reliability can be encapsulated in CCSVS space links. IP over space links are point to point, so you can apply header compression. That makes the whole IP UDP headers into a single byte. For example, if you use IPv6 with robust header compression. Next week in the IETF, there's a side meeting about deep space IP, and there will be a presentation on another version of or another header compression technique that will be presented. The key thing here is for IP to make it work in deep space is the fact that you have link up and link down because of orbiting devices, right? So either orbiters or planets orbiting. So in a normal IP stack environment, a router or forwarder that will be facing a link down, essentially it's in a forwarding table, the destination becomes unreachable. So it drops the packet and sends back an ICMP message error back to the source. We don't want to have this in deep space because a link up and down is normal. So what you do is you do essentially what MRO is doing right now with L2 frames, CCSVS frames, or BP, you do store and forward. So you essentially, instead of dropping the packet and sending ICMP error message, you actually just store the packet until the destination becomes reachable again, and then you forward the packet. Is it complicated? 200 lines of C code we did for the prototype, and we're just fine. But obviously, if you take a router from Cisco or something, it won't work. It needs that. But those need that temporary store packets is only for forwarders that have interrupt links, right? So what that means is routers on the planet, on Mars or Moon or something, don't need to have that feature. It's only the ones that face interrupted links. TCP, as you know, doesn't work in space, and its in kernel is, forget it. But UDP works. Which brings us to QUIC. And so QUIC was invented by Google people. It's about 35% of the whole internet traffic right now. So it's been used. It's about 95% of traffic of Facebook. So QUIC provides reliable transport services. It's like TCP in that way. It's end-to-end, provides connection, so it has state between the two peers. A single established connection is actually like a pipe where you have multiple streams in it. And each stream, that's the name they created for QUIC, it's equivalent to a TCP connection by itself. So you could have a connection established between the two peers, for example, from Earth and the spacecraft. And that connection the lifetime of connection could be a year, full for the whole mission. And then each peer could use that pipe, that connection, and then send packet in either way, or packet or request or, data. So it's very well suited for spacecraft because they have multiple payloads and they have long-lived applications. So it's there. It's very efficient because it's a single handshake, one RTT going, and then given what I just said, you can even establish the connection while the spacecraft is on Earth before it's launched. And then you continue that same connection while in space. So the single handshake provides both the QUIC itself and TLS handshake within a single RTT. So you get a security association right away between the two peers in one RTT. If for whatever reason the connection got down, given that the two peers know each other because they have a security association, then you can reestablish the connection, and the first packet you're sending to reestablish the connection to your peer can actually have data in it. It's called zero RTT. So you can actually send data at the same time that you are reestablishing the connection. it keeps the connection, and that's you were referring to IP mobility. So in IP, when you change IP addresses or ports, someone has to manage this problem, right? So we tried with IP mobility, so handling mobility at the IP layer, and we got no deployment. So what people do is we do it on the application layer. So therefore, when you move your cell phone from Wi-Fi to 3, 4, 5G, some application works, some application doesn't work. And then some OS provides some kind of features, but the right place to actually manage this is the transport layer. And QUIC does it very well. Because one of the reasons is that the connection, that the information that identifies the connection in QUIC is not the source and destination address and IP ports. It's connection ID that is opaque within the QUIC connection. So the connection ID doesn't change because of your changing your IP address or port numbers. So again, well suited for space. If the spacecraft is cruising and then land on Mars, and then got an IP address from the Mars infrastructure, no problem, QUIC will handle this. QUIC have mandatory security, reliable transport. It fixes reordering, lost application. So from the application layer point of view, if anything of this happened, it just managed that. So you don't need to care about if your packet is lost, it has been duplicated, is coming in wrong order. You can also configure QUIC for non-reliable, where you could have the actual ACK, but it doesn't provide the services that I just described. It's user space, so you don't need to change the kernel. You don't need to wait Linux new kernel version for something. It's just user space, easy to deploy. It carries HTTP over QUIC, so you can reuse any HTTP framework that we're using today. So it will be way simpler to develop applications for space. It can carry other apps, media, tunneling, whatever. And that is inside the same connection. So you can have media and then HTTP traffic and some app transfer, all this, file transfer, all this within the same connection. And obviously that connection is essentially a state in the two peers. You have many implementations in C, C++, Rust, Go, Python, Swift, Haskell, which have integrated in all HTTP software, browsers, curl, Nginx, Apache. And, my first slide usually for this presentation is, I'm not talking about the internet in space with users browsing to Mars, right? I know you know that, so I didn't say it, but okay, so don't come to me and say, my browser doesn't work in deep space. Yeah, I agree. That's not what we're talking about. We're using the IP protocol suite and stack, but not the typical applications we use today. So, does QUIC work for deep space? The answer is no, by default, because the current default, when I talk to the QUIC experts in the ITF and other places, they try to, shave, milliseconds in connection time. So we're not in this environment. So what happens is the assumptions that are in the defaults of a QUIC stack are for internet use. For example, they have to, for different reasons, they have to estimate the RTT, but you need to start with a value. And then that value is actually used, and then you change the value as you go, as you discover the RTT. Well, the default value to start with is, depending on the implementation, but it's around 200 milliseconds. So after 200 milliseconds, it starts transmitting packets because it hasn't received the return. Change that value. So we end up having to change 5 parameters, transport parameters in QUIC to make it work for very long delays. And you have to simplify the congestion control because the way congestion work on the internet is essentially you want to avoid routers to queue packets, right? That's what congestion control is. And the way we work with transport in the internet is when the clients discover congestion, it just pays down. Everybody pays down, therefore the congestion disappears. But in deep space, you will accumulate packets in routers because that's the store. Okay? Therefore, you need to simplify the congestion control that is used in QUIC. That's the key thing, right? So if you do that, and by the way, QUIC can use proxies. So there's different deployment scenarios. You can have QUIC proxies as space edge, inside orbiters. There's all kinds of ways of doing it, pros and cons, but I'm not going to this. So we tried it. We did a HTTP request and response with 10 days RTT, and it just worked. The first two packets is the connection establishment. The last two is the connection close. And there's a kind of extra stuff here, but don't need to look at this. The key point here I want to make is the connection establishment is only need to be done once, for a long time, and connection close at the same time. So it's really two packets, the get and back in the response. 10 days RTT. So if you want to deploy HTTP in applications in deep space, what you need to do is HTTP itself doesn't have any notion of time. There's only a few HTTP headers, such as cache control and expires, that have a time here. So you just need proper value or just don't use it. But the key thing here for HTTP clients and servers is they typically have timeouts. So you need to change the timeout. If you use curl, you just use -m and then the timeout being the largest RTT you have for your connection. At the level of QUIC and IP, all those, they don't know and they should not know that there's link interruptions. So when you calculate the RTT, you need to consider the worst case. So for example, if there's delay to Mars for 20 minutes for one way, but then the orbiter takes, gives you a window of 15 minutes every 6 hours, then you need to calculate that. So the total RTT is in the orders of multiple hours. But if you set that in the configuration of QUIC and the client and servers, then you're fine. They won't time up. So if you want to design a space application using HTTP, REST API, JavaScript, you just need to have the right design, which is completely asynchronous, local references to, assets. So, I don't know if you want to do, images and stuff like, HTML pages. But if you do, you make sure that they are not going to be sent on the deep system, and you set the timers properly. You can even use some web optimization, WASM or HBAC, but network management. SNMP uses UDP. In the protocol of SNMP, there is no timeouts or anything. So it's only the client. And we tested it. 4 hours one-way delay, 8 hours round trip time. Did SNMP get? You could do put. Whatever you do with SNMP standard, just works. NetConf is the new way to do network management. SNMP is still used probably like 80%, 90% of the networks nowadays, but NetConf is the new kid. NetConf by default works over TCP or SSH. That doesn't work in deep space, so you need to run it over QUIC. Or you use RESTConf, which is NetConf over REST over HTTP. SSH, we try to make it work in space, and it doesn't work. We tried various ways, forget it. There's an initiative right now of using SSH 3 over QUIC. Will be discussed next week in the ITF. Maybe that would be possible. But so, short summary. I haven't touched a lot of other topics, and I'm happy to answer. I'll try to answer. So temporarily storing IP packets in forwarding nodes until the links are back up for only the forwarders that have interrupted links, setting appropriate quick parameters or use UDP-based protocols and applications. And you properly design applications to be asynchronous and large numbers, then the Internet Protocol Suite can be used end-to-end in space. And that's it for me. And there's another announcement like Erik. So there's a deep space IP. There's a deep space mailing list in the ITF, and we are meeting Wednesday next week from 8 to 9:30. Look at the program for the room. Thank you.
Thank you, Marc. All right. So we have some time for questions and interactions between the audience and the panel. Let me just put this here. So who wants to start shooting some questions? Yes, Felix, please go ahead.
Bullseye here, right?
Maybe a question to Marc. The solution to say, okay, I just store my IP packets in my router is somehow for me changes behavior of the expected behavior of the protocol. So you might have some IP packets where you want to have this behavior, you might have other packets where you don't want to have this behavior because you expect a normal IP behavior. So I'm wondering if this is something you somehow need to make configurable, may have to signal somehow. This is an IP packet I want to store, this is an IP packet I want to forward it. And the second question also related to storage. As you said, we have no notion of time. So VP, we have the time to for the bundle. That's quite important because you don't want to have your data sitting forever in your router. So there must be a way to get rid of packets which are sitting too long waiting to be forwarded.
Yeah, I know. I'm noting. Every time I have questions, I note them because it's like, now I got disturbed, so I forgot the second. Whatever. It's a good question. I don't know that we need this, what you're saying about signaling IP storage or not. I don't currently see any issue or any need for that.
Well, I might expect that I'm sending an IP packet and it's basically routed immediately end-to-end, like normal IP traffic.
Mm-hmm.
Now, this link might not be available. So in this case, I might say, okay, if there's no link, please give me an error message and say there's no end-to-end connectivity available because the packet will not be relevant anymore in a few days or whatever. Or you would say, I store this because this link is not available. So I store your IP packet and send it forward whenever the link becomes available. So as a user, I might need to choose what I would like to have for this specific traffic I'm sending. So how can I control that?
Well, it's a good question. I don't know. Not sure the use case really, but I'm not sure. I'm not sure there's a need for that.
You just store them all?
So storage, included in this, some slides I have is about forwarding policies. So the storage is just one piece of it. What you actually have is an IP node with forwarding policies. Actually, BP needs the same thing. I actually wrote a draft on this presented at TVR, I think some time ago. But because as soon as you have storage, you need to make decisions, forwarding decisions, right? For example, if the storage is full, whatever is BP or IP or whatever, what do you do, right? Link is up. Which packets or bundles are you forwarding first, right? So you need forwarding policies, right? Mm-hmm. So that's related to that question, right? So you would need, whatever you do, BP or IP, some forwarding policies in the network to decide what you need to do in case of, to make decisions, right? So and that thing is same for BP and IP.
This is why we're working on the quality of service.
Exactly. What you have in IP.
I'm asking you, what are you doing in the case of IP?
Well, but IP, there's you already have all this tool set in IP, right? You can configure router with all kinds of, queuing disciplines. There's a rich set of things, and you can filter by, source, destination address, diff source bits. There's a whole flow label in B6. There's a whole set of tools already for doing those kind of decisions.
But as IP packets are received,
yes,
should they all just be dumped into the store, assuming there's room? Or does it need to be evaluated by inspection on a frame by frame basis?
well, I think that's the decision of the network operator, right?
That's a policy.
Right, that's policy.
So then
It's the same problem,
do
right?
you apply your policy by inspection on every frame? Or would you want an IP extension header that says this frame is storable
Well,
for this amount of time?
maybe. I'm not sure it really needs that. I don't know.
Nothing in your testing so far suggests one thing or the other. Because you're just storing everything right now.
Right. I'm the bullseye, so I'll get all the questions.
Yeah. More questions, maybe?
No, you had another question. I'm
No,
forgetting.
another question was about the time to live. Yeah, so in the bundle you have a time to live, so you
Right.
get rid of the bundle after.
Oh, okay.
So you have this IP, you don't have it.
And the IP layer,
Yeah.
the transport layer you have.
Time to live?
Well, not time to leave, but there's time in the transport, right?
But it's then again something defined by policy, network policy, how long you keep on your IP packets. Well, with a bundle, I can kind of decide by application and say this is traffic which is relevant for 10 minutes, the other one is relevant for 1 PS, whatever.
So what's the time you put?
It depends on my type of traffic.
Okay. And the actual RTT, right? The actual
Yes.
time of the
But I might say
the expected time, right?
yes, something I either get rapidly or forget about it. Yeah.
I think the time that you're talking about at the transport layer, first of all, it's stored at the endpoints.
Yes.
Secondly, it's about like timeouts for retransmit on ACT segments,
And
that kind of stuff.
yeah, all those kind of.
None of the nodes in the middle that are storing IP frames have any access to this information.
No.
Because it's not in the data plane of the transport
No,
payload.
it's fully encrypted and quick. There's no way you can see it.
Even in TCP though, or whatever, there's no, it's not exposed.
Yeah.
In fact, it's not even present to be exposed.
Yes, right. Well, there's negotiation of those, but
You just made me think of like, I think RFC 791, the original IP v4 draft. I think TTL was originally actually a
Yes.
1 second
Yeah.
thing. Yeah. And it was
yeah,
like-
1 second per op.
yeah.
but
At V6 we changed it to hop count. Yeah.
but the reality is all of count.
So 256 seconds.
Yeah.
55 seconds.
Yes, Scott.
Quick is end-to-end retransmission, right?
Yes.
So I've got a 4-hop connection from AP to C. B is an orbiter and C is an orbiter and that here. What do I do about computing my retransmission time at the center?
The timers?
What's my retransmission timeout value at the center?
Well, what you do is essentially you put the RTT being, the expected RTT being
across
The whole path,
hops to
the whole path, yeah,
right, okay.
because it's
That argument
end to end.
varies between
Yeah,
20 minutes and 4 days.
yeah,
Because of
yeah,
context.
Yeah.
So you just pick the largest?
yes.
So you just retain everything at the center for 4 days?
Well, as soon as you have X, then, yeah, and the X,
Because it's going to change, right? It's going to, like, right now it's 25 minutes.
Mhm.
10 minutes from now it's 4 days.
yeah,
Right? So, and then 4 days from now it's going to be 10 minutes.
Mhm.
So,
and then when you receive X, you don't need to keep the data because you know it's being
you
transferred.
didn't get the acts, right? They got lost.
Sorry?
Long
Data's
time
not
for
lost.
the retrans-
Yeah, you're going to try to retransmit because it's lost data, right? So your retransmission timeout on for retransmitting, for acknowledging and retransmitting the data, you're going to hold on to things for 4 days?
You hold on until you receive the X, which tell you get,
Right.
you get the
So,
data. The source,
right. So if
The other
transmission within the network, it might have reached from A to B to C, and from C to D, it did not succeed. And C could retransmit it, but it can't because it's end-to-end retransmission from A,
Right.
correct?
right.
So
It's not,
why
it's
is it
not
not
up by
superior?
up.
Why is it not superior to retransmit from C rather than from A?
It's a different design. The other way you could do is to have proxies in PAT,
Okay, right. And so if you have proxies, if you have like a proxy from A to B,
which
proxy-
is,
which is good, but then you have a protocol that conducts those proxies.
yeah.
That's what bundled protocol is.
Yeah,
Right.
there's pros and cons with proxies.
It's the thing that conducts the proxies.
Yeah, there's pros and cons in deploying proxies in there. So I'm not sure the
All
right.
So one other point on this then is IP over space links, because it's point to point, you can compress the header down to a single byte.
Mhm.
So it's point to point from A to B, but once it gets to B, it's a different point to point because it's from B to C. So how does B know what the destination is so that it can map it to its connection to C? Because it only got a single byte, right?
Start again. The context of header compression is within the peer-to-peer link. So if you have another peer-to-peer link, it's a different context. You start over.
Yeah, sure, but how does it know which peer-to-peer link to map it to once it gets to B? Because it has lost the original
Right.
final destination.
So the way header compression works is on peer-to-peer links is that the other peer that received the data essentially recreate the IP packet.
And it's
right?
able to recreate the IP packet because of
The context between the two peers, so the link. And then the next up, they will do the same. They will negotiate a context, then do the same. So it's really one link per link header compression. It's not header compression end to end.
right. Okay, so it needs to retain those IP address relationships over time so that it can remap all the way from the end to the end, right? So if there's IP mobility, doesn't that sort of break that?
No, because it's only in the link. It's only related to the
The
link.
compression still works, but how does it know which peer to talk to? It's the address. It's the IP address of C, for example, is changed.
You can't handle the IP
I think
migration
there needs to be some additional
at endpoint.
state.
because you had a
Well, it's a different context. It's just a different context. For the header compression, it's just like another packet, which is not related to the other one.
So as part of the negotiation of the compression context for that final link, you would also have to run whatever would be necessary to discover that an endpoint's IP address had changed. The connection ID migration for quick on that final link.
No, header compression is at the IP layer. So
And you uncompress at each hop
yeah,
and
it's just
recompress for a new context for the next hop.
for the next one. Yeah,
And then compress. But like if IP migration has occurred for the final hop,
it's different IP packets because
Correct.
the IP address source destination ports are different.
Right.
So therefore, it's just another packet.
It gets lost.
No, it's a new context because it's a new packet, right? So on the point link, it will create a new context because it's just not the same context.
But it has the penultimate router, the penultimate node, not the ultimate destination, penultimate node receives the packet.
Router of peer-to-peer link.
Router C of peer-to-peer link in this case receives it,
Yep.
decompresses it using the header compression context from B to C.
Which for C, right? Okay.
Yeah.
Yes.
It then wants to recompress using a compression context from C to D for ultimate delivery to D. Correct me if I'm misunderstanding you correct.
That's where I'm going, yeah.
Yeah, and then, okay, so in that time, if D's IP address has changed,
The router IP address.
Oh, the final destination. In this
the
case.
final destination IP address
Okay.
could be the router, it had a NAT change or whatever it is.
Okay. Well.
So you're saying in that period, in that final link negotiation, because it's peer to peer, you have to also discover that D's IP address has changed.
No, because that packet doesn't change, right?
But the packet doesn't have the IP address in it anymore because it's been compressed out.
It gets restored at every stage. You have to propagate the context end to end.
Yeah, but
No,
on the B2C, on the B2C hub, it's not there anymore, right?
Correct. But the necessary context information is actually at C. He's saying you decompress
At each
node.
Yes.
and there's a new, completely different context
So-
for each peer-to-peer.
So C has access to the entire logical original packet as originally sent.
Right.
Of course, the first
Including
packet
C
you're
has
sending.
access to the original IP address, but that IP address is no longer valid because this D is no longer at that address.
Sure, but for the purpose of header compression, this is, not related. It continues to forward the packet.
It's going to go to the wrong place, right?
It will not be deliverable to D.
Oh, well, that's not related to header compression. It's just related
Correct.
to IP mobility.
Correct.
Okay.
Exactly.
So
Yes.
there's nothing about header compression in this.
Correct.
Okay.
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 On a similar topic, there is a natural tension between addressing and identity.
Yeah.
Ability
Where ITF is locator versus, so the whole
also
debate for.
comes into play for security and identity authority delegation too. Is that something that's been looked into at all? Is having a stable identity separate from address?
Well, it's IP. It's like Quick, right? So Quick use TLS. So what you have is TLS.
Sure. But what I mean is,
Well, whatever TLS provides you, you get
has
it.
it been
You're
investigated?
not end-to-end quick, you're not end-to-end TLS.
Well, there's an assumption. DNS names get used for many purposes, and you can use a DNS name as an identity without using it with DNS. You can use the DNS name without using DNS. But has that been investigated at all for utility?
I'm not sure I understand your question.
A DNS name is just a name. It's a way to ensure uniqueness. But there's implications to having a DNS name because you want to use DNS to look it up, but you don't have to. But this is where there's a contention, like you were saying earlier. Tools have timers, tools have assumptions, and I imagine that with DNS names, it's similar. Tools might have assumptions that if I get a DNS name, I'm allowed to use it with the DNS.
Somewhat. Now, it's possible to use IP address, to use IP without names.
Sure.
But reality is it assumes names everywhere, right?
Yeah.
And names provide you something, right?
Extension.
So I put the assumption that, you should use DNS. The key here is don't try to do resolution over deep space links. That doesn't work. So what you need is essentially, similar to what you were, showing on the surface you have a DNS local infrastructure, right? But you don't. You avoid having DNS resolution. So what you need to do is essentially pre-caching of names you need on the surface.
You've been able to convince tools to use timers appropriately. It's also an exercise, I think, to convince tools to use names appropriately as well. Like theoretically, yes, but the tool might have embedded assumptions that.
Yeah, we did once a small test bed with what I just described, which is kind of an isolated network. I actually wrote a draft about that, and it worked fine. But you just need to be careful for how you pre-cache stuff. The DNSSEC, if you're using DNSSEC and you're making sure that you have local verification, there's a few things to be careful of, but it actually works.
Yeah, I'm wondering what happens if packets are coming out.
There's two other panel members, right?
That's a fair point.
I'm on the jury.
As a moderator, I would like to prioritize questions for Erik and Leigh.
Please, Simon.
To leave Marc breathe a bit.
Please, Simon. No, I'm fine.
Quick one. It's kind of related. So
Yeah.
what do you
Go ahead.
on
I was sure that would happen.
quick level, just if packets comes out of order?
Sorry.
If you get out of order of packets on a quick level, can you handle it?
Yeah. Quick does that.
Has a packet number.
It's actually, I don't want to go deep into Quick, but Quick has a notion of frames. That's actually what is being sent. And the Quick stack actually could, for different connections or different streams within the connection, can assemble multiple frames within a single packet. And then if you lose a packet, you're actually using one or two or three frames that may be from different streams, but it handles all this.
But you can also set the reliability on a frame by frame basis.
On a stream by
stream basis, but that means that unreliable frames will not be packed in with. They could be packed in with reliable datagrams, but they would not. But if they get lost, they don't need to be retransmitted.
Exactly.
So you have the option to pack them.
Exactly.
Unreliable frames in one packet that could get lost, and reliable frames in a packet that will be retransmitted.
And that's unreliable is typically is like for streaming, for example, where you may decide as an application to decide that if I don't receive one frame of a video, I don't care, and so
this is the datagram extension inside of Quick.
I will try a panel question. When we look at proposed space networks, one of the things that we see is a desire to have smaller telecommunications packages on rovers, on smaller orbiters, and so on, with the idea that if you have some communications infrastructure, then that makes it cheaper for everybody else. But in addition to that, what you tend to see is telecommunications payloads, science payloads being duty cycled so that they are constantly turning on and turning off. And so at the panel level, could we have a discussion that says in these respective areas, how do you handle the case where you have endpoints coming and going in a somewhat unreliable way as individual components power themselves on and off or react in some particular way? So that is, how do we do it in one way? How do we do it in the other way? Panel question.
I think those don't work.
You can speak up.
Oh, okay. So if you got a relay spacecraft, you got two relay spacecraft going around Mars, and you've got maybe 3 or 4 rovers on the surface, and some of the rovers want to send their data to the orbiter every time the orbiter goes overhead. Other rovers can't do past 4, 7, and 9 because that's when they're charging their batteries, or they're busy drilling a hole in a rock or something, and they're not at the right angle to make the connection. The data rates are negotiated by the link. So you can't even predict what your data rate is. It all depends on antenna pattern and so it's very unpredictable. And usually the contact graph plan is the way we handle that. The orbiter, the rover team gets a list of all the orbiter passes that are going to go overhead. The orbiter has already decided that for some of the passes it can handle uplink and transmission, relaying data from the surface. For other passes, it's busy doing atmospheric science or taking a picture of something that puts the UHF antenna in the wrong direction. And so they winnow that down to, okay, these are the passes where we go over that orbiter, the orbiter goes over that lander, that the landers could possibly use to uplink data. Then the lander teams look at those and say, okay, out of all these passes, here's the times we would like to send data, and here's an estimation of how much data we have and we'll be able to send. And then that all gets put together into a overall data flow plan that we put in contact plans, in contact graphs. And today what it is that each spacecraft gets a stored sequence, which is essentially like a contact graph for that particular spacecraft or lander. And then they operate according to that contact plan. And then if a relay orbiter has stored up a whole bunch of data, and one of the landers, one of the orbiters, one of the relays customers, if you will, has an emergency or has high priority traffic, then the prioritization and quality of service part of VPN will take over and put that at the head of the queue. And all these mechanisms could be reinvented, and we could do it all with UDP quick and everything else if you've got a lot of millions of dollars and another 10 or 12 years to redesign everything we've been designing for the last 10 or 12 years. Have at it. I think that there's a lot of and the other thing too is I don't want to retransmit all the way from the other end to the destination. I want to do custody transfer. I want to send it from A to B to C. And if the C to D hop goes down and there's a bunch of errors, the D spacecraft needs to do the retransmission from the C spacecraft and not have to go all the way back to the source at the A spacecraft. And that was one of the other design features. We don't do end to end. We do hop by hop retransmission. TLS, I'm just thinking it was 8 years. It was 8 years to get to Saturn. So we do our zero round trip time trick with your TLS. And does that, TLS have to last for 8 years? Is that a secure way of doing things? Or do we have to, how often would we have to change that TLS business and, do another round trip time handshake with UDP Quick if it was going out to Saturn or Pluto or something?
I think for duty cycle concerns, I think I would draw a distinction between planned and unplanned. I think the vast majority of cases are probably planned. Unplanned cases are probably indistinguishable from other sorts of errors. In which case, you would find yourself retransmitting, and you'd find yourself reaching out through alternate channels. If there's sort of the equivalent of an S-band TT&C channel, see if that's access for something like that, or trying to talk to an omnidirectional antenna instead of some other directional thing. But I think for the sort of planned cycle changes, I feel like one huge element that is absent from all of these things, it's actually implicit in the way the networks are operated, is today is a multi-stakeholder trusted control plane authority, right? It's implicit in a single operator domain. You trust your own stuff. Somebody sends you a control plane message, you trust it. If you have a lot of spacecraft that are trying to relay things to each other, knowing when someone is going down or not going down, that information, if it's part of a regularly sort of planned set of cycles, like your sort of sun charge cycle for orbiting the Earth or something like that, that information could be distributed to all of the receivers that might need to know about it, possibly well in advance. But you also need a way to trust that those messages are true and correct for that craft. And that is something that is implicit probably in every mission, implicit in every deployment. Having a generalized framework for that would be a huge boon, I would think.
Although even just a quick sort of add to that, even unplanned changes mean that the contact may not have shown up because of the unplanned change. But then does that not mean then that you just queue it against a subsequent future contact and hope that that future contact comes up? And that becomes the recovery mechanism is fall to a future contact, or does that get into congestion territory?
I think that's your DTNMA. Isn't that your autonomous design where you have like backup plans where if you lose connectivity and you can't communicate with your control plane, you need defined timeouts where.
I have a question about autonomy.
Is it? I would think of it as related, but
unplanned. I wanted to point out that the unplanned occurrence of a Mars spacecraft going into safe mode. Safe mode means it thinks something is wrong, or its star tracker has failed, or it's gotten confused by something, and it gets scared and it doesn't know what to do. So it turns the spacecraft so solar panels are pointing at the sun. It's completely lost track of where the Earth is because it doesn't really know where it is. It just knows where the sun is, and as long as it's got its solar panels out, it's going to keep its battery alive, and everything's going to be happy until Mom comes to the rescue. Now, Mom all of a sudden is now on a 70-meter dish, talking 10 bits per second up, 7.125 bits per second down, and it takes 45 minutes for a complete telemetry frame to come through to figure out what's going on, and so you know how to get out of safe mode. And so there's a whole unplanned events are not just the communication protocols. They reach right down into the link layers, into the physical layers. And that's another thing that we take into consideration with DTN and our contact plans that I'm not sure how we would do with Quick.
Guys, we have 3 more minutes for the panel. Do you want to add something there, Marc, or
so much
another question otherwise? Yeah, maybe Felix, you have.
You're a brave man.
Yeah, so I'm not very familiar with Quick. I have a question on the transport semantics. The nice thing about bundle protocol, you put an application data unit, which can be even very, very large. Yeah, and it can be kind of self-contained data, which makes a lot of sense for spacecraft. You put everything together, which together makes some sense. And either gets bundled or you don't. I would assume Quick is more kind of stream oriented. So I'm also wondering how the unreliable mode works. So if you have losses in between, so are you still are you submitting really a packet or a replication data unit and get parts of it, or how does it work with Quick?
I read RC about unreliable mode, but I haven't tried it in terms of see how it actually behaves. So I'm not sure I can fully answer your question how it behaves. But we can read the RC. But
it's not only for you, maybe some.
There are streams that are open bidirectionally, and the streams are there's byte streams and datagram streams. Datagrams will have like implicit record boundaries, basically.
Size?
No.
Okay.
It's negotiable, and in fact, you can in the opening sequence, you can one side can tell the other, this is the max memory I'm allocating you. So if you want to send more than this, go away.
Okay, but that's not related to datagram. It's related to the actual connection.
There's many settings at many layers.
Okay.
Yes. And then, but otherwise, broadly, the streams inside of Quick are just are an endless byte sequence. Those byte sequences are chunked up into frames. The frames have their own flag structure, and they can be tagged for reliable retransmission or not. Frames are packed into packets. Packets have their own packet number, all of which are encrypted. So you can tell by the packet number when a packet number is reported as missing, my understanding, my recollection of RFC 9000 is that the source knows which frames it put into which packet. If any of the frames were marked for reliable transmission, it has to remember them, right? So when it figures out which packet number is missing, it knows which frames were missing, and it can like repack those frames into a new packet or split them into 3 new packets or whatever it deems necessary. And they each get new packet numbers, and then those get sent, and they can tell if those get lost again. But if for unreliable frames, the additional overhead tracking and ACK mechanism is not used.
So that would need to have a kind of mechanism to do some synchronization of my screen by data to detect my record boundaries or whatever I have. Yes.
Datagrams, I think they allow you to specify record length endpoints. Yeah, but even for like DNS over TCP, record lengths get added to streams all the time.
I was going to add one thing about time to live, because in the internet, time to live was put in so we don't have routing loops and that sort of thing. In the space world, time to live is it's an application data unit level construct. It's when is this data legitimate? I mean, it's useful or not. I can have an ephemeris file that's good for the next 2 weeks, and so its time to live is going to be like 2 weeks. But then I can have some interactive spacecraft commands or things like that if it doesn't get it in the next 10 minutes, forget it, because your moment has passed. And so how does Quick handle application time to live as opposed to the individual?
Not the way you describe. I don't think there's a thing Quick the way you describe it.
I think the application interface to Quick is you get to just pick what kind of stream you want to open, what kind of session you want to open, like a byte stream or a datagram stream. You can get notifications of delivery. You can set some flags
on a datagram by datagram basis,
or on a frame by frame basis. If you get stuff delivered in a byte stream to you. But if any of those things need to be retransmitted, or if they have like you need to add your own application time information into those frames.
Yeah, the way you describe it, I don't think Quick provide that.
Yeah, it doesn't.
That would have to be something about the application. So
we have to invent something above that to do what we're doing with VPN now.
It'd be a part of the payload in a Quick context.
We are on time for closing the panel, so I think we can thank the panel with a big applause. Thank you for the discussion.